£14 million. That's how much Project Inversion is going to cost. It is a huge amount of money, and in this video I'm going to share why it costs that much. If you're new to this series, we're planning to drive a Formula car upside down for 5 seconds with aerodynamic force alone. So the main costs, as you can imagine, are the car, building the tunnel and hiring the location. And just the size of this project is astonishing. 1,330 tons of temporary steelworks, 131 tons of temporary aluminium works, 49,000 meters squared of plywood. That's the same as 7 football fields. And all of that plywood has to be held together with something, almost 500,000 screws. It's a whole load of materials, but we're using as many standardized off-the-shelf parts as possible, with our structural engineers having planned for as much reuse as we can. So let's start breaking down the costs, and let's begin with the car. We're using the Empire Wraith hill climb car as the base for Project Inversion. It's light, has high downforce at relatively low speeds to accept the electric motors and batteries I described in the last video. And as an added bonus, it was designed by our head aerodynamicist Willem Toet, so he knows the car's design better than anyone. As race cars go, the Wraith is actually pretty well priced, costing £65,000 brand new from Empire. As you might have seen in the second video of this series, Willem has made significant developments to the car, mostly aerodynamic, but we'll also need to make changes to the suspension setup and geometry because of the unusual curvature the car will be turning across and the camber required. So an estimate of the aero mods comes in at around £35,000. But the main cost of the car modifications will be the electric motors and batteries. As discussed in the last video, we're likely going to be using incredibly small yet powerful motors, which fit inside each of the 4 wheels. As you can imagine, this type of technology doesn't come cheap. And we're actually yet to have a precise cost that we can share, but it will certainly be in the hundreds of thousands of pounds to develop. So that's the car done, but we still need to test that it and the driver work upside down. And we also need to check that the downforce numbers that have come out of the computer correlate with the actual downforce the car generates. So we'll need to test that as well. First up, we'll build a mechanical simulator that can flip the car upside down while static. Here we'll be looking to make sure all of the systems on the car work properly upside down. We'll make sure that nothing unusual happens to the suspension, the motors and the battery, all things that have not been designed to run upside down. Even small things like the seat belts could be an issue. Normal adjustable race belts have excess belt when you tighten them, which usually just sits neatly on the driver's chest. But when we're upside down, any excess belt would fall in front of my face, blocking my view. And that's not something we want to discover for the first time when we're doing the stunt. And this simulator will help me get accustomed to driving upside down in a race car, which while it won't be the first time, it will be the first time I actually meant to do it. I imagine it's going to feel very unusual hanging upside down, and that it will take a bit of getting used to. I want to be sure I'm completely comfortable hanging upside down, as I'll need 100% of my mental capacity to ensure I drive the car properly and keep an eye on all the telemetry that I'll be shown. So to make a simulator that can replicate loads similar to the event itself, and to purchase another chassis to use, as we'll be building the actual Project Inversion car at the same time, we estimate it will cost around £280,000. Once we've got the car and the driver comfortable working inverted, it's time to make sure all of the aero work is producing as much downforce as predicted. The car will be covered in sensors to ensure everything is working how we expect. One of the most important sensors will be strain gauges in the push rods. As you might imagine, these measure the strain or the load going through the push rods, so essentially logging the car's mass plus downforce. The first testing will be done on a normal piece of asphalt, something like a runway. This is something that F1 used to do a lot to test aero. Hire out a runway, do a straight line test that runs through a range of speeds, make an aero change and do the same again. And they do this to get real world data to show how different parts and setting affect the downforce levels. F1 doesn't do this anymore, but you might see drivers running at set speeds during a Friday practice session. When they're doing this, they're after the same data. Then, once the structure is built, we'll do some extra testing. This means we can check the car running in the curve of the tunnel. This is going to be critical, as the curve of the tunnel is going to negatively affect the amount of downforce we create. weight. All in, we expect this testing to cost us another £170,000 if everything goes well. So that's about it for the car. Next, the real cost, the location and the structure. Now, to boil down all of this data and all of these costs, we had to use a lot of data analysis. And similar to the majority of skills we used on this project, you can start learning them yourself with Brilliant, today's sponsor. Check this out, it's Brilliant's course on data analysis fundamentals. Everything you need to know about averaging, relationships in data, and understanding uncertainty in data. We've had to do a lot of that in this project. In understanding aerodynamic data, load cases, costs, tolerances, the lot. These are all aspects that our team cannot get wrong, and it all stems from a great understanding of the basics. Brilliant have thousands of visual lessons from foundational and advanced maths to AI, data science, real engineering, and more, with new lessons added monthly. To try everything that Brilliant has to offer for free for a full 30 days, visit brilliant.org/driver61 or click on the link in the description. The first 200 of you will get 20% off Brilliant's annual premium subscription. Thanks again to Brilliant for sponsoring this video and all of the series about Project Inversion. And with that, back to the costs. The location for Project Inversion will likely be driven by the headline sponsor, so it's difficult to estimate what that will end up costing. It may be a large part of the budget, or it may end up costing very little. So for the purpose of this video, we've left it out. The location will also have some effect on the cost of the structure itself. Building this on a racetrack, a car park, or a runway will be cheaper than on less consistent ground. And the location's temperature and the difference between the minimum and maximum temperatures and things like wind speeds will all make a difference to how the final structure will be built, and therefore the final cost. But the bulk of the costs for Project Inversion won't change. And the bulk of the costs are in the core materials for the structure itself. To remind you, the tunnel is 700 meters or 2,300 feet in length. It's 7.5 meters or 25 feet in height. It's going to use 1,500 tons of temporary metalwork, 7 football fields of plywood. The raw material cost is massive, not to mention the huge team required to put it all together. And so the following numbers have been put together based on the car with a speed of 44 meters per second, which is a very conservative 98 miles per hour. In fact, we're likely able to bring the speed down somewhat below 90 miles per hour, once we've confirmed the downforce levels in a real-life test. Therefore, we may not quite need the 700 meters to enter the tunnel, transition to inversion, drive upside down for 5 seconds, and then transition back down. And of course, we could reduce the time upside down, although I really don't want to do that. However, this would reduce the cost. So here's the shopping list for the Project Inversion tunnel, and let's start with the framework. First, we need 3,000 meters of the VarioKit main beams, seen just here. Then we need 6,400 meters of the truss struts, seen here. Next, it's 1,500 meters of the support beams for the bottom of the curvature just here. We'll also need 5,000 meters of X-beams to support the track surface down its length. And we'll need 9,000 meters of scaffold lacing elements to brace the X-beams. And this all sits on 1,900 supporting sleepers, seen just here. So that's the framework, but now we need something for the car to actually drive on. We need the surface. The total area of the track is 11,000 meters squared. But in order to have the strength required and for the curved surface to retain its shape, the surface is actually going to be made up of 4 layers of 12mm plywood, screwed into place one after another. And that's a lot of plywood. In fact, it's 1,160 sheets of extra large 2.4 meter by 9.5 meter pieces. They're sheets that are 10 times bigger than what you'd get from your local hardware store. And they all need to be fixed in place with almost 500,000 screws. Duval, if you want to sponsor us, we'd be more than happy to talk. And with it all being screwed in place, we'll be able to reuse a lot of the surface. With us, Expedition Engineering have put a lot of energy into making this project as sustainable as possible. We'll also need to finish the surface. And as we don't have any racing regulations to adhere to, we're aiming for the highest grip possible, although we're yet to make our final decision. And of course, the tunnel itself is a huge advertising board. So there'll be some costs involved in printing on the surfaces where necessary, although this will be a small percentage in the whole project. We'll also need some accelerometer sensors in the structure, so we can understand if the structure is moving in the wind or with the car, and by how much. So they're the raw materials, but we also need to have a huge team of people to put the structure together over what is likely a couple of months. and surveyors to ensure everything is safe before we're given the green light. That all said, the budget for the structure is massive, coming in with some safety margin at almost £14 million, which is roughly 30% for the frameworks, 40% for the plywood, and another 30% for the assembly. That's a massive number, and one we need serious backing to make happen. Now, these numbers are quite conservative and have been put together with us buying all of the parts without any partnerships. And with our 5-second goal, it would be possible to reduce costs somewhat if we rented the frameworks, quite drastically if we partner with suppliers for the framework and the surface. This is the final installment for the moment of Project Inversion. If you're yet to see the other videos where I outline the project, detail the car, tunnel and powertrain, please check out this playlist here. Thank you very much for watching, and I'll see you next time.